Welcome to the deep dive. Today, we're really digging into a critical challenge facing AI right now. How do you actually build a production-grade defense framework for large language models?
It's a huge topic. We're seeing LLMs everywhere,
Yeah.
right? From simple tools to apps with real autonomy.
And that expansion, that access and autonomy, well, it makes them incredibly attractive targets for attackers. The source material we're looking at today really hammers this home.
Absolutely. And the core idea, the thing you have to grasp right from the start, is that basically no one knows how to completely stop zero-day or brand new LLM attacks. Not with 100% certainty.
Okay, so perfect prevention is off the table.
Exactly. And that's a fundamental shift. It pushes AI protection into the same kind of category as, say, traditional malware defense. It's not about finding a magic bullet. It's about managing risk.
Through better observation, multiple layers.
And, crucially, speed.
Yeah.
Rapid response and constant adaptation. That's the name of the game.
So our mission today is to really unpack a specific architecture designed for that reality. We're going beyond just talking about individual detection models, right?
Yeah, forget the best classifier debate for a moment. We're looking at an integrated end-to-end system. The framework we're dissecting combines three core platforms: threat intelligence, data, and release.
And we're assuming our audience, you listening, already have a good handle on MLOps, security basics. We want to focus on what's unique here for generative AI.
Precisely. The key contributions are really operational. First, there's this systematic threat intelligence capability. They call it IntelOps. It's built for automated prioritization, and it has a pretty novel way of quickly translating new attacks into actual defense signatures.
Okay, speed again. And the second contribution.
That's on the data side, a unified data correlation framework. Think multi-source big data analysis, better labeling, and crucially setting complex criteria before you release anything new.
Which helps prevent those nightmare scenarios where an update breaks legitimate use cases.
It's exactly. Preventing deployment-induced false positives is critical. And the third piece, which from an engineering standpoint is maybe the most interesting, is the deployment strategy itself. An immutable multi-version architecture.
Immutable, meaning once it's out, it doesn't change.
Right. It allows for things like seamless shadow testing, running a new version silently alongside the old one, and instant, totally predictable rollbacks if something goes wrong.
Yeah.
That's massive for keeping production stable.
All right, before we dive into those three platforms, let's spend a bit more time on the why. Why is securing LLMs so different from, standard network security or older detection systems?
Well, it really boils down to the adaptive nature of the fight. Think about the cybersecurity ODIA loop. Observe, orient, decide, act. Security teams are constantly in this loop with attackers.
It's a continuous cycle.
It is. And if you pour all your effort into building one perfect model, it's inherently fragile. The moment an attacker finds a way around it, you're back to square one, playing catch-up.
So the focus has to shift.
Completely. It shifts from the quality of that single snapshot model to the speed and efficiency of your entire ODA loop. Can you adapt faster than the adversary? That's the real question.
And the actual defense layer, the thing doing the blocking and filtering, that's the guardrail concept mentioned in the paper.
That's the term they use, yeah. Guardrails are essentially the deployed layer that mediates inputs and outputs. It enforces your security and safety policies.
So that includes things like sanitizing prompts.
Right, filtering out malicious stuff, monitoring continuously, but also things like adversarial training, trying to build some resilience into the model itself. It's a broad concept.
But even with guardrails, you run into the fundamental limits of machine learning for detection, especially with new threats. Let's talk about that generalization problem.
Ah, yes. That's a huge hurdle. ML models, generally speaking, don't handle out-of-distribution inputs very well.
Yeah.
Ode inputs.
Things they haven't really seen in training.
Exactly. And adversarial attacks are basically designed to be owed. So a novel attack, a 0-day. There's a good chance the model misclassifies it, often thinks it's harmless. Attackers are actively looking for those blind spots.
And even if a model could theoretically detect everything, you hit that operational wall. The false positive rate, the FPR.
Oh, absolutely.
Right.
That FPR has to be incredibly low in production. You simply cannot have your security system constantly blocking legitimate customer actions.
It breaks workflows, causes outages.
It can be catastrophic, especially for critical systems. And think about it. Actual attacks are usually rare compared to legitimate traffic. It's a needle in a haystack situation. So you need super high precision, very few false alarms, which makes it incredibly hard to also maintain high recall, meaning catching most of the actual attacks.
And the paper is pretty blunt. There's no known way to guarantee 100% prevention against all adversarial attacks right now.
Nope. Especially things like prompt injection that exploit the model's understanding of language itself. Simple pattern matching just doesn't cut it.
Which brings us to this conflict, this tension between MLOps wanting to release quickly and security QA needing to be cautious.
It's a classic bottleneck.
Hmm.
Rolling out a new ML model safely takes time. You need careful observation, gradual rollouts, maybe over days or even weeks.
Why so slow?
To make sure it doesn't suddenly start blocking things it shouldn't, right?
Yeah.
You need to watch its behavior on real traffic. But that careful, slow validation process clashes directly with standard engineering cycles that want rapid QA for everything else.
So, okay, perfect prevention is out. ML models are tricky to roll out quickly and safely. Where does that leave us?
It leaves us with the practical reality that the response mechanism has to be fast and reliable. The framework argues the only viable solution is ensuring rapid response and timely protection through continuous updates.
Getting protections out before an attack becomes widespread.
Exactly. You need a high operational tempo, get initial protections, maybe simple signatures out fast, while you gather data and train the more robust ML models in a safer, staged way.
Okay, let's get into the first platform then. Threat intelligence operations, or IntelOps. This sounds like where the system gets proactive.
It is. IntelOps is designed as that first line of defense. Its job is to ingest raw intelligence about new threats and vulnerabilities, figure out what's most important, and turn that into actionable protection quickly.
Prioritizing the stuff that's actually likely to show up in the wild.
Precisely. It's basically adapting standard cyber threat intelligence, CTI, practices specifically for the AI world. It's a structured pipeline, highly automated with objective scoring, aiming for that rapid signature deployment we talked about.
And it runs as a continuous cycle. The paper mentions 5 components.
Yeah, it's a tight loop. It starts with component 1, automated collection and monitoring,
So pulling data from where?
all over. Olson feeds think archive papers, security blogs, vulnerability databases, but also commercial feeds, closed sources, internal research. They even mention using specific tools like GenReader to help deduplicate and structure the incoming info consistently. Little details, but important for automation.
Okay, so you collect everything. Then component 2, prioritization and analysis.
Right. Raw intel hits an automated scoring and classification engine. Based on the score, it gets routed. High priority stuff goes straight into a queue for human analysts.
Which leads to component 3, analysis and reporting.
Yep. There's often an initial automated triage, maybe using an LLM to summarize the threat. But then, crucially, a human analyst reviews it, validates the technical details, digs deeper.
And component 4 is where the action happens, detection and data generation.
This is the output stage. 2 key things come out. First, immediate detection signatures, usually wire IRA rules, for rapid defense. Second, actual attack implementation code, which is used to generate training data for the ML models later.
And finally, component 5 closes the loop, feedback.
Exactly. IntelOps constantly reviews telemetry for the data platform, what signatures are hitting, what are they missing. This feedback refines the initial scoring and prioritization, making the whole system smarter over time. Hashtag 2.1 taxonomy and prioritization.
You mentioned scoring and prioritization. Central to that seems to be this dynamic taxonomy they use.
It really is the organizational backbone. It's quite clever, actually. It merges existing standards like the OWASP LLM Top 10, MITRE Atlas for adversarial ML tactics, and the NIST taxonomy.
So it combines different views of the threat landscape.
Yes, and critically, it bridges traditional security concerns like data theft with AI safety concerns like generating harmful content. In production, you need to defend against both malicious intent and accidental harms. This unified view is essential.
And this taxonomy feeds the priority intelligence requirements, the PIRs.
Directly, the PIRs dictate what intelligence gets collected and focused on. They're structured around basically 2 things: vulnerabilities specific to certain models or applications, and the general tactics, techniques, and procedures that TTP's attackers use.
How does that prioritization work in practice? Can you give an example?
Sure. Let's say a new vulnerability is discovered. If it affects a major, widely used frontier model that's integrated into critical systems, that gets a higher priority score just based on the potential impact of the potential blast radius.
Makes sense. What about TTPs?
Okay, take indirect prompt injection. That's where an attacker hides a malicious prompt in data the LLM might retrieve later, like a web page. That TTP gets a high priority because, well, it's seen frequently in the real world, and it's tricky to catch just by looking at the initial user prompt.
So the PIRs reflect both impact and likelihood or frequency.
And they're constantly reviewed and updated. Sometimes they even have time limits, like focusing heavily on a specific new threat for 90 days to ensure rapid mitigation before it potentially fades. Hashtag 2.2, the automated scoring algorithm.
Let's drill into that scoring algorithm. This sounds like the engine that actually translates all this intelligence into a number that tells analysts what to work on first.
It's key for making the process scalable and objective. The formula they use is PPT in TFEG plus 0.5 MEG plus S plus 0.5 E3T3. It spits out a score from 0 to 5.
Okay, let's break that down. AVG is the average priority of the TTPs involved, and it gets full weight, a coefficient of 1. Why weight the technique highest?
Because the technique is often more fundamental and transferable than the specific target it was first found on. A clever way to bypass guardrails on Model A can probably be adapted to Model B relatively easily. So focusing on the TTP gives you broader, more lasting defense.
Right, whereas ERVGAV, the score for the affected models or applications, only gets half weight, or zero point 0.5.
Reflecting that, yeah, the target matters, but the method is often the more general threat. Then you have CO source credibility.
How trustworthy is the information?
Exactly. A verified report from a known security firm scores higher than, say, a theoretical idea on a preprint server like Arxiv that hasn't been peer-reviewed.
And the last term, ease of implementation, also gets half weight, 0.5. What goes into that?
The dollar tries to capture how likely attackers are to actually use this technique. It considers things like, is the target system easily susceptible? Are there easy ways to detect this with simple signatures? If so, the risk is lower. Is exploit code already floating around?
So is it trivial to pull off, or does it require, like, nation-state resources?
Basically, yes. It combines susceptibility, detectability, and availability of tools. It helps focus resources on threats that pose a practical near-term risk. Hashtag 2.3, converting intelligence to actionable defenses.
So the algorithm flags a high-priority threat. What happens next? The human analyst steps in, but with some help.
Right. There's often LLM-assisted triage first. An LLM might generate an initial summary, what the threat is, how it works, potential impact, maybe even suggest detection ideas. It gives the analyst a head start.
But the human is still the final gatekeeper.
Absolutely critical. The analyst validates everything, refines detection signatures, thinks about edge cases, potential false positives in specific contexts, assesses the real operational impact. Their validated findings go into the internal intel hub, the central knowledge base.
Okay, let's talk about those immediate defenses. YRA rules. Why use something relatively simple like YRA when you're dealing with complex LLMs?
Speed and predictability. YIRA rules combining text, hex patterns, regex, logic can be written and deployed very quickly. They offer immediate mitigation for known patterns without waiting for a full ML model retrain and rollout cycle.
Good for template attacks or specific keywords?
Exactly. And critically, their behavior is predictable. You know exactly what input will trigger a YIRA rule block. They give you much higher confidence for rapid deployment compared to a probabilistic ML model update, which might have unexpected side effects.
Like an emergency brake.
A very precise emergency brake. But they still need testing. Every new YARA rule is run against the huge corpus of past prompts in the data platform.
To make sure it doesn't accidentally block legitimate traffic?
Precisely. Maintaining that near-zero FPR is paramount.
So YRA is the quick fix. But for long-term, robust defense, you need the ML models, and for that, you need data.
And this is where IntelOps gets proactive again. They have an automated attack data generation framework. It takes the theoretical vulnerabilities identified by the analyst and systematically turns them into labeled training data.
So you don't have to wait for attacks to happen in the wild to get training examples?
Exactly. You break that reactive cycle, you can start building defenses for new techniques almost as soon as they're understood theoretically.
What can this data generator do? Does it just create simple attack prompts?
It's more sophisticated than that. It can apply various obfuscation techniques, paraphrasing, character substitution to known jailbreaks. It can create multi-turn conversational attacks where the malicious part is spread across several interactions.
Making it harder to detect with simple filters.
Right. And it's built for scale parallel processing and meticulously tracks metadata. What technique was used, the harm category, generation parameters. This detailed provenance is vital for training effective models.
Okay, let's move to the heart of the system, the data platform. You described it as the central nervous system. It's where everything comes together.
Pretty much. It's the single source of truth for storage, aggregation, enrichment, labeling. All the decisions made by IntelOps and the release platform rely on the data managed here.
And the architecture is key. You mentioned it's warehouse-centric, using something like Snowflake?
Yes, a distributed data warehouse. This was a deliberate choice, prioritizing flexibility over traditional, rigid ETL rack transform load pipelines you often see in older security setups.
Why the move away from traditional ETL?
Because LLM data is messy and changes constantly. New prompt formats, new languages, new attack structures pop up all the time. Old school ETL pipelines with fixed schemas break easily or require huge effort to refactor. The warehouse approach lets the transformation be much more dynamic.
How so? How does it achieve that flexibility?
Transformations are done largely using SQL, but heavily augmented with UDFs, user-defined functions, and especially external UDFs.
External UDFs, what do they allow?
They're powerful. They let you call external services like AI models for labeling or translation, or even custom Python code directly within your data warehouse queries. You can run complex processing on the data without having to constantly move massive data sets in and out of the warehouse. It's much more efficient and adaptable.
And all this data lives in one place. The data pool. The benefit there seems obvious for correlation.
It's huge. It breaks down silos. You can easily correlate everything.
Sure.
Customer prompts and guardrail responses, anonymized of course, public data sets, labels generated internally by humans or models, translations, the attack data from interlops, plus detailed logs from all guardrail versions, current, old, and even upcoming ones in testing.
So you can compare how different versions would have handled the same prompt.
Exactly. Offline evaluation becomes much easier and more comprehensive. Hashtag tags 3.1 prioritization and labeling workflow.
So the data platform holds all this info. What are its main jobs? You mentioned prioritization and labeling.
Right. First, it runs prioritization tasks across all the data. Using dynamic views, it combines historical knowledge with live operational data to figure out what needs attention now.
What kind of tasks?
Things like identifying prompts in different languages, running automated labeling routines, classifying language, evaluating performance against current and future guardrail versions. That's key for release decisions, scoring prompts against third-party tools, scanning everything against the latest signatures. It's constantly assessing the data pool.
And this feeds into a central knowledge table.
Yes. Think of it as the master record for each prompt. It aggregates all the labels, scores, signature matches, where the data came from everything keyed by a unique prompt ID. This unified view allows for really complex and fast-changing prioritization rules.
Which leads to the most critical output, labeling. Getting the ground truth right.
Absolutely fundamental. If your labels are wrong, your ML models will be wrong, and your whole defense is compromised. But labeling for security has unique challenges.
Such as?
Well, first, the accuracy needed for benign data is insane. If you want your system to have, say, a 1 in a million false positive rate, your labels for benign data better be at least that accurate. Any error there directly impacts your FPR.
Wow, okay. Pressure's on the labelers.
Immense pressure. Second, you need to identify novel attacks. You can't just rely on one tool or one model for labeling. The golden label needs to be a consensus, aggregating inputs from instructed LLMs, human reviewers, signature hits, maybe feedback from the interlops team who generated some of the data.
So you need humans in the loop, but you can't have them look at everything. How do you prioritize their effort?
The platform has to be smart about highlighting what needs human eyes. Things like prompts that were actually blocked in production, samples where automated tools disagree or have low confidence, edge cases that don't fit neatly into the taxonomy.
And human review isn't just about fixing labels.
No, it's crucial for quality control. Detecting label drift, where the automated consensus starts diverging from human judgment. Diagnosing why a model made a mistake, was it the model or bad labels? And refining the threat taxonomy itself based on real-world examples. Humans are essential for that deeper understanding.
Okay, we've got intelligence, we've got data and labels. Now the final piece, the release platform. This tackles that huge operational risk and update going wrong and causing chaos.
Exactly. The nightmare scenario is pushing an update that introduces a wave of false positives, blocking legitimate users, breaking critical applications. This platform is designed specifically to prevent that, enabling safe, continuous deployment.
And the core idea is this immutable concurrent architecture. Can you explain that again?
Sure. Instead of updating a component, like an ML model or a set of signatures in place, you treat every version as immutable, unchangeable once built. When you need an update, you deploy the new version alongside the existing stable version.
So you might have multiple versions running simultaneously in production.
Potentially, yes, managed by an orchestration layer that directs traffic. It sounds complex, maybe resource intensive.
Yeah, I was wondering about the overhead.
But the benefits are massive. First, seamless shadow deployment. You run the new version silently, feeding it real traffic, but not acting on its decisions, just logging them. Second, gradual rollouts. You can shift a small percentage of traffic, monitor, then increase. Third, and this is the killer feature, instant deterministic rollback.
If the new version misbehaves, you just flip a switch and all traffic goes back to the old stable one.
Instantly. No redeployment needed, no downtime. It completely de-risks the release process, especially for probabilistic things like ML models.
And crucially, it decouples the ML team's careful, slow validation cycle from the faster pace of regular engineering releases.
That's the operational magic. Engineering can push urgent bug fixes or infrastructure updates without waiting for the ML team's multi-week validation process, and the ML team can take the time they need without blocking engineering. It increases velocity for everyone, safely. Hashtag tag 4.1 signature and model update processes.
Okay, so let's look at how updates actually happen. There's a difference between signature updates and model updates, right? Signatures are faster.
Much faster. Generally, signature updates coming out of IntelOps are the rapid response tool, used for quick fixes, maybe plugging a gap while a new ML model is being trained. Because Yardi array rules are predictable, there's higher confidence in deploying them quickly.
But still staged, right? Not just pushed straight to prod.
Oh, absolutely. Rigorous staging is essential. First, in the internal Snowflake environment, they run a delta analysis. Compare the new signature package against the historical prompt corpus. Does it trigger on anything unexpected? Any spike in potential FPs?
Catch problems before they leave the lab.
Exactly. Then it moves to preview staging. Here, the full guardrail stack with the new signatures is run against test traffic, maybe rescanning recent production data. Finally, the production rollout is gradual, carefully monitored, maybe starting with a shadow deployment just to be extra safe.
Okay, that's signatures. Now, model and logic updates. These are the riskier ones, taking days or weeks.
Yeah, because a new ML model or changes to the core orchestration logic can fundamentally shift detection behavior in ways that are hard to predict perfectly. Any change triggers the creation of a completely new, immutable guardrail version.
And that new version gets deployed first to pre-production, running alongside the current stable one.
Right. The key then becomes differential analysis. The new version is bombarded with a curated dataset from the data platform high-priority prompts, known attack types, tricky, benign samples.
And you're not just looking at its accuracy in isolation, but specifically how its predictions differ from the current production version.
That's the critical part. The threat intelligence team pores over those differences. Where does the new model disagree with the old one, especially on benign traffic? That flags potential new false positives.
I thought this is clever if they find systematic FPs during this stage.
They often push a signature update first to explicitly block those specific FP patterns before letting the new ML model proceed further.
Using the fast deterministic fix to patch the hole before rolling out the slower probabilistic change.
It's a smart way to stabilize things. Once issues are resolved to an acceptable level, the new version finally moves to production, but always starts in shadow mode.
So it sees real traffic, makes predictions, but doesn't actually block anything yet.
Right. This allows them to gather real-world performance metrics, FPR at the target operating point, recall on actual attacks, any drift in overall flag rates before a single customer is impacted. Only when that shadow analysis confirms stability and safety does the gradual migration of actual user traffic begin, with that instant rollback capability ready just in case.
So putting it all together, this framework really feels like a mature blend of established cybersecurity principles, the ODA, loop, focus, immutability, threat intel, adapted specifically for the challenges of AI.
It really is. The beauty is how the three platforms, IntelOps, Data, and Release, work together to create this closed loop. Intelligence feeds prioritization, data enables validation and labeling, and the release platform ensures safe deployment. It systematically shortens that cycle from identifying a threat to having a safe, effective protection in place.
Moving from, say, an ArcSIF paper describing an attack to deployed defense potentially in days, not months.
That's the goal. And it creates this self-reinforcing cycle. Every interaction, every piece of data, every near miss feeds back into the system, making future defenses stronger. It tackles the vulnerability window by using signatures for speed and staged, validated model updates for robustness.
But the authors are clear this isn't the final answer. There are still big challenges, areas needing more research.
Definitely. This is a rapidly evolving field. They highlight a few key areas.
One was improving cross-model generalization. What's the issue there?
Well, ideally, defenses you build and train for one LLM, say, from one vendor, should work reasonably well on a different LLM, maybe an open source model or one from another provider, without needing a complete retraining effort every single time. Achieving better generalization would massively speed up deployment across diverse environments.
Makes sense. They also mentioned scaling the threat intelligence processing.
Yeah, as attackers get smarter, maybe even using AI to find vulnerabilities, the volume and sophistication of threat intelligence is just going to explode. The IntelOps platform needs to keep scaling to handle that flood without overwhelming the human analysts.
And adapting to totally new kinds of attacks.
Right. We need better algorithms, better classification techniques to handle attack methods that don't fit neatly into today's categories. The system has to constantly learn and adapt its fundamental understanding of what constitutes a threat. Hashtag tagout outro.
So, stepping back, what's the big takeaway here for you, for our listeners who are operating AI systems at scale?
I think the core message, connecting it to the bigger picture, is this. As AI gets more powerful, more agentic, and integrates deeper into everything we do, the attack surface just keeps growing, and the stakes get higher. What this paper really demonstrates is that solid, principled engineering, things like immutability, rigorous data management, and especially building for rapid response, isn't just nice to have, it's essential. It's how you safely accelerate your own ODLU to stay ahead of attackers while still deploying powerful AI.
It really drives home that point about response over perfect prevention, which leads to a final thought for you to consider. We know technologically we can't guarantee 100% prevention against novel attacks today. So the question becomes, how should organizations balance their resources? How much do you invest in building these robust adaptive response frameworks like the one we've discussed, which focus on speed and deployment safety, versus how much do you invest in potentially higher risk, basic research, chasing that goal of complete foundational prevention?
That's the multi-million-dollar question for AI security strategy right now.
Something to definitely mull over. Thanks for joining us on the deep dive.